Whether you are looking at the biological neural network of a human brain or the silicon logic gates of a computer processor, both systems share a specific operational weakness. When forced to process arithmetic in a state-dependent sequence, the machinery eventually stalls. Long before the invention of the microchip, educators had to confront this processing bottleneck in their students. In 1897, Russian mathematicians A. Malinin and K. Burenin published an arithmetic textbook designed to ruthlessly optimize how the human mind calculates. They identified a core problem in standard subtraction, the necessity of borrowing across positional columns. You cannot resolve the calculation in the tens column until you have already altered the state of the hundreds column. Take the equation 112,436 minus 57,268. To solve this, a student must constantly update multiple changing variables. They borrow from the tens, cross out the hundreds, carry a 1, and track a chaotic cloud of slashes and dots floating above the original numbers. This forces the human mind to perform a state-dependent operation, where the resolution of one column is entirely blocked until the adjacent column is modified. Malinin and Burenin proposed that subtraction can be entirely bypassed by treating it as a specialized case of addition. Their solution, detailed in section 29, relies on a concept called the arithmetic complement. Applying this 1897 algorithm removes the need for borrowing. The minus sign rotates into a plus sign, transforming the expression into a standard addition problem, 12,436 plus 42,732. This transformation allows a student to process math using the exact same logic gate architecture that runs inside modern computer processors. Converting the operation into addition makes every column independent, removing the computational cost of tracking the borrowed state. To understand the mechanism, we look to section 26. The text redefines subtraction algebraically. Instead of taking away a quantity, you are finding an unknown addend that, when combined with the subtrahend, equals the minuend. This leads to the arithmetic complement, the exact difference between a number and the clean unit of the next higher order, like 100, 1,000, or 100,000. Suppose we need the complement of 57,268. Normally, we would drop down 100,000 directly above it to find the difference. But doing this with standard subtraction would trigger the borrowing process we are trying to avoid. The textbook provides an algorithmic shortcut. You subtract every digit of your number from 9, except for the final digit on the right, which you subtract from 10. Subtracting from an array of 9s guarantees that the upper digit in every single column is equal to or larger than the lower digit. You calculate straight down without a single borrow. 9 minus 5 is 4, 9 minus 7 is 2, 9 minus 2 is 7, 9 minus 6 is 3, 10 minus 8 is 2. The complement is 42,732. This hack deliberately shifts the burden away from volatile working memory, relying instead on simple, independent factual recall. To use this complement, we must manipulate the original equation while maintaining a strict mathematical balance. We start with our minuend, 112,436. We subtract 100,000 and then immediately add it back. The net value remains unchanged. Then we place our subtrahend, minus 57,268, at the end. Using the rules for parentheses found in section 31, we group these terms into two isolated brackets. The first bracket simply strips the highest order unit away from the minuend. Subtracting 100,000 from 112,436 requires 0 borrows. The second bracket is the arithmetic complement we solved using the 9s and 10s shortcut. The first bracket leaves us with 12,436. The second bracket leaves us with 42,732. Combined, they give us the final sum of 55,168. By intentionally manipulating the initial conditions, we mathematically guarantee that the tedious process of borrowing is fully eradicated from the workflow. This algebraic effort is primarily useful for scaling complex calculations. Section 29 provides a compound problem, 54,371 minus 3,548 plus 5,513 minus 479 plus 364 minus 17. Solving this sequentially forces the solver to switch cognitive modes back and forth between adding and subtracting, increasing the chance of an error. Applying the arithmetic complement transforms the chain. Every minus sign becomes a plus sign, and every subtrahend morphs into its complement. Standardizing the dataset entirely into addition removes the need for mode switching. The horizontal string rearranges into a single vertical stack. You calculate downward once, and the problem resolves to 56,204. Standardizing operations into a single type allows an algorithm to scale without increasing the complexity of the core task. Decades after Malinin and Burenin, computer engineers encountered these same limits in early hardware. Physical circuits handle state dependency poorly. Waiting for a borrow signal to travel between logic gates slowed the processor and invited electrical noise. Computer science solved this by adopting 2's complement, an architecture that avoids physical subtraction entirely. If we place the 1897 algorithm side by side with a modern binary process, the parallel is exact. The first step of 2's complement requires the computer to flip the bits of the subtrahend, changing the zeros to ones and the ones to zeros. In binary, flipping the bits serves the exact same mathematical function as the 1897 trick of subtracting every base 10 digit from 9. The final step of 2's complement is to add a 1 to the end of that flipped binary string. Adding 1 in binary is mathematically identical to the Russian textbook's rule of subtracting the final right-hand digit from 10. A modern computer executes the exact same invert and add logic that 19th century students were taught to do with a pencil. Malinin and Burenin used foundational axioms to design away inefficiency. Human working memory and silicon logic gates share the same operational bottlenecks. Optimizing these systems involves refining the structural algorithm, bypassing the need for more raw processing power. Whether for a student in 1897 or a 21st century processor, elegant mathematics is a tool for navigating the physical limits of our hardware.